It has been over 40 years since a single spacecraft flew past Uranus. Just one, and we never went back. Not because we lost interest, but because what we found there made scientists quietly admit we may have gotten this planet completely wrong from the very beginning. Uranus is not just a distant cold rock spinning alone in the dark. It is a world tilted on its side, hiding diamond rain beneath its clouds, and holding secrets that could rewrite how we understand ice giants entirely. If you want to explore the universe one planet at a time, hit subscribe, because we are just getting started. There's a planet in our solar system that humanity has visited exactly once. Not landed on, not orbited, just passed by, a fleeting glance from a machine traveling at 35,000 miles per hour, cameras clicking as fast as they could before the window closed forever. That planet is Uranus. And in the decades since that single encounter, something strange has happened. The more we studied the data from that brief flyby, the more we realized we did not understand what we were looking at. Scientists have quietly, carefully begun to revise nearly everything they thought they knew about the seventh planet from the Sun. This is not a story about a boring blue ball floating at the edge of the solar system. This is a story about one of the most misunderstood, most extreme, and most financially fascinating destinations in all of space exploration. The solar system was born approximately 4.5 billion years ago from a vast cloud of gas and dust swirling around a young star. Jupiter and Saturn grew massive enough to pull in enormous quantities of hydrogen and helium, becoming gas giants. But Uranus and Neptune are different. They formed in a region so cold that water ice, ammonia ice, and methane ice were solid and abundant. These two planets built their bulk from ice, which is exactly why modern scientists classify them as ice giants, not gas giants. That distinction changes everything about how these worlds behave and what lies beneath their clouds. Uranus sits approximately 1.8 billion miles from the Sun. Driving at 60 miles per hour without stopping, it would take roughly 3,400 years to get there. Light from the Sun takes 2 hours and 40 minutes. Temperatures in the upper atmosphere drop as low as minus 371 degrees Fahrenheit. The coldest planetary atmosphere ever recorded, colder even than Neptune, which is farther from the Sun. The leading theory for why Uranus holds so little internal heat involves one of the most dramatic events in solar system history. Billions of years ago, something enormous, possibly an object the size of Earth, slammed into Uranus and knocked it completely sideways. Today, it rotates with its axis tilted at approximately 97.8 degrees, essentially rolling through space like a bowling ball. Each pole experiences roughly 42 Earth years of continuous sunlight, then 42 Earth years of total darkness. No other planet behaves this way. That single ancient collision defined this world for billions of years. Now here's a question almost nobody thinks to ask. Is space hot or cold? The answer is stranger than most textbooks admit. The vacuum of deep space sits at approximately minus 455 degrees Fahrenheit, barely above absolute zero. But in a vacuum, there is almost no matter to transfer heat into your body. You would lose heat only through radiation, the slowest method possible. Meanwhile, the side of your body, facing the Sun, could reach hundreds of degrees from solar radiation. Near Uranus, where the Sun is 2 billion miles away and barely brighter than a star, solar energy is about 390 times weaker than on Earth. You would be in the coldest, darkest, most hostile neighborhood in our solar system. And yet the inside of the planet tells a completely different story. Beneath the pale blue-green clouds, that color comes from methane absorbing red light and reflecting blue and green, lies a world of almost unimaginable pressure and heat. There is no solid surface. The atmosphere simply grows denser and hotter as you descend, transitioning into a superheated fluid made of water, ammonia, and methane in a state that does not exist anywhere on Earth. Scientists call it superionic water. Water molecules break apart under the pressure, Oxygen atoms lock into a crystal lattice, while hydrogen atoms flow freely like a liquid. Temperatures in this region climb to thousands of degrees Fahrenheit. The contrast between the frozen exterior and the raging interior of Uranus is one of the most striking paradoxes in planetary science. And deep inside that inferno, something extraordinary happens. The methane molecules in the atmosphere are torn apart by the pressure. Carbon atoms, crushed millions of times beyond anything achievable on Earth's surface, crystallize. They become diamonds. Real, physical diamonds, not formed in a mine or a laboratory, but in the crushing depths of a world 2 billion miles from Earth. These diamond crystals sink slowly through the liquid mantle over thousands of years, accumulating near the rocky core. Some scientists theorize the core of Uranus is surrounded by an ocean of liquid diamond, with solid diamond icebergs floating on its surface. This was confirmed in laboratory experiments at the Stanford Linear Accelerator Center in California, where researchers used lasers to compress carbon-rich material to pressures matching those inside ice giants. The diamond rain on Uranus is real. The magnetic field of Uranus is one of the strangest in the solar system. On Earth, the field aligns closely with the rotational axis. That is why a compass points north. On Uranus, the field is tilted at nearly 60 degrees from the rotational axis and does not even originate from the center of the planet. It is offset, shifted away from the core, as if two competing magnetic systems are fighting for control. A compass near Uranus would not point the wrong way. It would spin and drift with no logic whatsoever. As for life, Uranus has carbon, nitrogen in the form of ammonia, and water. The upper atmosphere is too cold, the deep interior too extreme, and the middle layers too violent for anything we would recognize as biology. But the universe has surprised us before. Europa and Enceladus were once considered dead worlds. They were not. The waters of Uranus are not like Earth's oceans, but they are there. If a human being attempted to descend into the atmosphere of Uranus, the winds alone would destroy almost any spacecraft ever built, reaching up to 560 miles per hour, nearly 3 times the force of Earth's most powerful hurricanes. Deeper down, pressure would exceed the bottom of Earth's deepest ocean within a few hundred miles of the cloud tops. Temperature would climb from minus 400 degrees Fahrenheit at the clouds to thousands of degrees in the mantle. There is no surface to land on, no moment of arrival. You would simply be compressed and vaporized as the planet swallowed everything you built. No human being could survive this. No spacecraft ever constructed could either. But understanding this, fully, precisely, scientifically, is exactly what drives the next great era of planetary exploration. And the bill that comes with it is something worth examining very carefully. This is where the conversation changes. Because the science of Uranus is not just a matter of intellectual curiosity. It is a matter of extraordinary financial scale. Every question we have just explored, the diamond rain, the sideways rotation, the magnetic field, the possibility of life, remains unanswered because we have spent almost no money studying this planet. And the numbers behind that neglect and the cost of correcting it are staggering. The only mission that has ever visited Uranus was Voyager 2, a spacecraft launched by the National Aeronautics and Space Administration in August of 1977. Voyager 2's total mission cost, accounting for its entire journey past Jupiter, Saturn, Uranus, and Neptune, was approximately $865 million in 1977, which, adjusted for inflation to today's purchasing power, represents roughly $4.5 billion. Of that total budget, the Uranus flyby itself represented only a fraction of the mission's resources, since the spacecraft had already traveled for 8.5 years and consumed most of its scientific operating budget by the time it reached the 7th planet. The encounter lasted approximately 6 hours. 6 hours of observation, 6 hours of data collection, 6 hours of photography and atmospheric sensing. That is all humanity has ever directly experienced of Uranus, purchased at a price of billions of dollars and nearly a decade of travel time. Since that flyby in January of 1986, the National Aeronautics and Space Administration has spent nothing, not a single dollar of mission funding, on a dedicated Uranus spacecraft. Other destinations were prioritized. Mars received rovers, landers, orbiters, and a helicopter at a cumulative cost exceeding $30 billion over the last 3 decades. Jupiter received the Galileo mission, the Juno mission, and is now the target of the Europa Clipper with a total investment approaching $8 billion. Saturn received the Cassini mission, which cost approximately $3.2 billion and spent 13 years studying the ringed planet in extraordinary detail. Uranus received nothing. In the entire history of space exploration, after that single flyby in 1986, no nation on Earth has sent a single dedicated spacecraft to study the 7th planet. This is beginning to change. In 2022, the National Academies of Sciences, Engineering, and Medicine, the body that advises the National Aeronautics and Space Administration on its long-term scientific priorities, released its Planetary Science and Astrobiology Decadal Survey, a document produced every 10 years that ranks the most important targets in solar system exploration. For the first time in the history of these surveys, a Uranus mission was ranked as the single highest priority flagship mission for the coming decade. The recommended mission, called the Uranus Orbiter and Probe, would consist of an orbiting spacecraft that would study the planet from above for multiple years, combined with an atmosphere probe that would descend into the clouds and transmit data before being destroyed by the pressure. The estimated cost of this mission, as outlined in the survey, is approximately $4.2 billion. That number includes spacecraft development, launch vehicle costs, mission operations over a roughly 13-year cruise to Uranus, and the scientific instruments needed to answer the fundamental questions about the planet's composition, magnetic field, ring system, and moons. For $0.2 billion. To put that in context, the United States government spent approximately $817 billion on national defense in fiscal year 2023. The entire annual budget of the National Aeronautics and Space Administration is approximately $25 billion. A Uranus orbiter mission at $4.2 billion would represent roughly 17% of the entire agency's annual budget, a massive commitment, but one that the scientific community has now formally declared to be worth it. The challenge is not the science. The challenge is not the technology. The challenge is the political will to maintain funding for a mission whose journey alone will take over a decade. To actually reach Uranus on a reasonable timeline, a spacecraft launched in the late 2020s or early 2030s would need to use a gravity assist from Jupiter, essentially using Jupiter's enormous gravitational field as a slingshot to accelerate toward the outer solar system. This is the same technique Voyager 2 used. Missing this launch window, which depends on the alignment of Jupiter and Uranus in their respective orbits, would delay the mission by years and significantly increase fuel costs. The launch vehicle of choice for such a mission would likely be the Space Launch System, the National Aeronautics and Space Administration's heavy lift rocket, which has a launch cost of approximately $2 billion per flight. Alternatively, a commercial heavy lift vehicle, such as the SpaceX Starship, if it achieves full operational capability in the coming years, could reduce launch costs dramatically, potentially to $200 or $300 million per flight. This is not a trivial difference. A reduction in launch costs of $1.5 billion could free up enough funding to add additional instruments, extend the mission's operational lifetime, or even add a second probe. Beyond the flagship mission, scientists have proposed several smaller and less expensive concepts for studying Uranus. A flyby mission, similar to the original Voyager 2 encounter but using modern instruments, could be achieved for approximately $500 million to $1 billion and would provide vastly better data than the 1986 flyby, simply because the technology available today is incomparably more advanced. A small orbiter mission without an atmosphere probe has been proposed at a cost of approximately $1.5 to $2 billion. These options represent a spectrum of scientific return versus financial investment, and the debate within the planetary science community about which approach to take first is active and ongoing. There's also the question of opportunity cost. Every dollar spent on a Uranus mission is a dollar not spent on Mars, asteroid sample return, or outer planet moon missions. The decision to prioritize Uranus in the decadal survey was made against scientific evidence showing that ice giants represent the most common type of large planet in the galaxy. Surveys of exoplanets have revealed that planets in the size range between Earth and Neptune are extraordinarily common. Our solar system, with its 2 gas giants and 4 rocky planets, may actually be the unusual case. Ice giants appear to be the default setting of planetary formation across the universe. Understanding Uranus is not just about understanding one neglected planet in our own backyard. It is about understanding the dominant class of world in the cosmos, the kind most likely to exist around other stars, and possibly most relevant to the origin of life somewhere else in the galaxy. The $4.2 billion price tag is not the cost of visiting one planet. It is the cost of understanding what most planets actually are. Uranus has been waiting in the dark for 40 years. Patient, silent, tilted on its side, raining diamonds into an ocean no human eye has ever seen, spinning its broken magnetic field through the cold void at the edge of our solar system. We flew past it once, for 6 hours, with cameras from the 1970s. And then we looked away. The universe handed us a mystery, and we set on a shelf. But the shelf is not permanent. The scientists who ranked Uranus as the top priority in planetary exploration did not do so by accident. They did it because they understand that the most important questions are often the ones we have been too busy or too cautious or too underfunded to ask. The answers are out there. They are 2 billion miles away, and they are waiting. If this video made you think differently about what is out there, about the worlds we have ignored, and the price we pay to truly understand them, then you are exactly who this channel was made for. Every week, we take you deeper into the universe, past the headlines and the textbooks, into the real numbers, the real science, and the real cost of human curiosity. Hit subscribe, turn on notifications, and come back next time, because what we are going to show you next will make Uranus look like a warm and welcoming neighborhood. The universe is stranger than you think, and we're just getting started.